An interval is said to be closed if both the endpoints are included in it. It is denoted by square bracket a comma b. If one of the endpoints is infinity or minus infinity, even then the interval is said to be a closed interval. An interval is said to be a half-closed or a half-open interval if only one of the endpoints is included. There are two types of half-open or half-closed intervals. If A is included, but not B, then the bracket is closed at A and open at B. It is denoted as shown. On the other hand, if A is excluded and B is included, then the bracket is open at A and closed at B. It is denoted as shown. An interval in which both the endpoints are excluded is called an open interval and is denoted as shown. Take a look at the table. The maximum value of sin theta and cos theta from 0 to 2 pi is 1. And the minimum value of sin theta and cos theta from 0 to 2 pi is minus 1. And if we increase or decrease the value of theta by an integral multiple of 2 pi, then the values of sin theta and cos theta do not change. This implies that the values of sin theta and cos theta lie between minus 1 and 1 for all theta belonging to R. In other words, the domain of sin theta and cos theta is the set of real numbers, and their range is the closed interval minus 1 to 1. Now, tan theta, which is equal to sin theta divided by cos theta, is defined when cos theta is non-zero. Now, cos theta is 0. When theta is equal to 2n plus 1 into pi by 2. Therefore, tan theta is defined for all theta belonging to the set of real numbers not equal to 2n plus 1 into pi by 2, where n is any integer. Or, tan theta is defined for all theta such that it is a real number and is not equal to 2n plus 1 into pi by 2, where n is any integer. This is the domain of tan theta. And the range is the set of real numbers R. Cot theta is equal to cos theta divided by sin theta. It is defined when sin theta is non-zero. Now, sin theta is 0 when theta is equal to n pi. Therefore, cot theta is defined for all theta belonging to the set of real numbers not equal to n pi, where n is any integer. This is the domain of cot theta, and the set of real numbers is the range of cot theta. Secant theta is equal to 1 divided by cos theta. This function is defined for all theta belonging to the set of real numbers not equal to 2n plus 1 into pi by 2, where n is any integer. This is the domain of secant theta. The value of secant theta does not lie between minus 1 and 1. Therefore, the range is the union of the closed interval minus infinity minus 1 and the closed interval 1 to infinity. In other words, the range is the set of all real numbers y such that y is greater than or equal to 1 or less than or equal to minus 1. Cosecant theta is defined when theta is not equal to n pi, where n is any integer. Thus, the domain is the set of real numbers not equal to n pi, where n is any integer. And the range of cosecant theta is the same as secant theta. Let us now see the behavior of trigonometric functions in different quadrants. Take a look at the table again. The value of sin theta increases from 0 to 1 and the value of cos theta decreases from 1 to 0 when theta increases from 0 to pi by 2. From pi by 2 to pi, the values of sin theta and cos theta decrease from 1 to 0 and 0 to minus 1, respectively. When theta increases from pi to 3 pi by 2, sin theta decreases from 0 to minus 1, while cos theta increases from minus 1 to 0. And in the fourth quadrant, the values of sin theta and cos theta again increase from minus 1 to 0 and 0 to 1 respectively. Similarly, the behavior of the other four functions can be seen in different quadrants. Observe that the values of tan x and cot x repeat after an interval of pi. However, the values of sin x and cos x repeat after an interval of 2 pi. Hence, the values of cosec x and sec x will also repeat after an interval of 2 pi. Let us now draw the graphs of the trigonometric functions one by one, beginning with sin x. Let us take the values of x as 0, pi by 6, pi by 4, pi by 3, plus or minus pi by 2, plus or minus pi, and plus or minus 3 pi by 2. We know that sin x is equal to 0 when x is equal to n pi, where n is any integer. Also, sin x is positive in the first and the second quadrants, and negative in the third and the fourth quadrants. Therefore, sin x is equal to 1 when x is equal to pi by 2 and minus 3 pi by 2. It is minus 1 when x is equal to minus pi by 2 and 3 pi by 2. Sin pi by 6 is half. Sin pi by 4 is 1 by root 2. And sin pi by 3 is root 3 by 2. Now, let us plot the values of x on the x-axis and the corresponding values of sin x on the y-axis. We get the graph as shown. From the graph, it is clear that the curve passes through the origin and the minimum and maximum values of sin x are minus 1 and 1 respectively. It is also clear that the domain is the set of real numbers and the range is the closed interval minus 1, 1. Let's now move to the graph of cos x. Again, let us take the values of x as 0, pi by 6, pi by 4, pi by 3, plus or minus pi by 2, plus or minus pi, and plus or minus 3 pi by 2. We know that the value of cos x is 0 if x is equal to plus or minus pi by 2, plus or minus 3 pi by 2, and so on. Also, the value of cos x is minus 1 if x is equal to pi and minus pi, and 1 if x is equal to 2 pi minus 2 pi. Cos pi by 6 is root 3 by 2. Cos pi by 4 is 1 by root 2. And cos pi by 3 is 1 by 2. Now, let us plot the values of x on the x-axis and the corresponding values of cos x on the y-axis. We get the graph as shown. Observe that the graph of cos x does not pass through the origin, and the minimum and maximum values of cos x are -1 and 1 respectively. Proceeding on to the next function. Let us take the values of x as 0, pi by 6, pi by 4, pi by 3, plus or minus pi by 2, plus or minus pi, plus or minus 3 pi by 2. Then, the corresponding values of tan x are as shown. Plotting the values of x on the x-axis and tan x on the y-axis, we get this graph. Observe that the curve of tan x passes through the origin. Next, let us draw the graph of cot x. Like in the earlier functions, let us assume the same values of x. Then, the corresponding values of cot x are as shown. Plotting the ordered pairs x, cot x in the Cartesian plane, we get the graph of cot x. Next, let us draw the graph of secant x. Take the values of x as 0, pi by 6, pi by 4, pi by 3, plus or minus pi by 2, plus or minus pi, plus or minus 3 pi by 2, plus or minus 2 pi. The corresponding values of secant x are as shown. On plotting the values of x on the x-axis and the corresponding values of secant x on the y-axis, we get the graph of secant x. From the graph, it is clear that secant x does not lie between -1 and 1. Lastly, let us draw the graph of cosecant x. Take the values of x as 0, pi by 6, pi by 4, pi by 3, plus or minus pi by 2, plus or minus pi, plus or minus 3 pi by 2, plus or minus 2 pi. The corresponding values of cosecant x are as shown. On plotting the values of x on the x-axis and the corresponding values of cosecant x on the y-axis, we get the graph of cosecant x. Observe that the graph of cosecant x also does not lie between -1 and 1.